So the data science workflow, the way I define it is you have step one, which is ingestion. Step two would be EDA, or exploratory data analysis. Step three would be the modeling. And then 4 is the conclusion. And what we're going to focus on today is really inside of here, ingestion and exploratory data analysis mostly. And part of that, when you go into exploratory data analysis, is visualization. And what is interesting about visualization is that there is a feedback loop that goes into a modeling and conclusion phase. So it's almost like you have an iterative process, right, where you're going closer and closer to the center when you're doing this. You start exploring the data. You may in fact go through and do some EDA / modeling to get to the actual modeling. We'll just call that MD, right? And a lot of times this exploratory data analysis here would be unsupervised machine learning. And with unsupervised machine learning, you can create clusters which will discover labels, which then later help you decide what kind of models you want to work on. So I'm going to go to this repo here, and I'll go ahead and put this into our chat window. So let's go here, put this into chat. And so this particular project is an interesting project because it covers a lot of the step-by-step workflow of a real-world data science project. So what I'm going to do is I'm going to scroll down. There's a lot of stuff in this notebook, but I'm going to scroll down to a section where we get into a real-world data science walkthrough. So let me talk a little bit about this process. So this is a social power NBA data science project, and some of the topics that are covered in this particular section are the data collection sources, importing and emerging data frames of pandas, how to create a correlation heat map, using Seaborn, using linear regression, using ggplot, k-means clustering, principal component analysis, classification with scikit-learn, regression, and then using Plotly. So to start with, this is the first part, which is really the painful part when you're working on a real-world data science project is how do you get the data? And a lot of times, if you're working on something that's interesting, like that you're personally passionate about, you're not going to get the data from Kaggle, right? Or a data set somewhere else that someone gave you. You're going to have to find it yourself. And that's what makes the project interesting is you have a hunch about something and you need to investigate it. And this is really, it's a form of journalism. It's like investigative reporting. And in this particular problem, I had been working at a sports social network for a few years, and I was wondering about how you could collect data that would answer questions about the influence of athletes in the NBA, and whether the influence on social media had an impact on their performance in the game, and then also whether it had an impact on their pay, and then how that led to valuations of NBA teams. So what I did is I didn't really have all of the answers yet when I started, but I had a lot of questions, which is a good place to start. And so what I did was first grabbed the attendance for teams in the NBA. I also looked at the players in Wikipedia. So Wikipedia is actually a very interesting data source that few people use, that's free, that has text inside of it. It has metrics around social media engagement. So you can think of Wikipedia as social media because of the fact that people are creating it, and you can consume the page views of how much people are actually visiting those pages, so you can figure out their popularity. So it's like a follower count. I also looked at Twitter. I looked at census data in the United States, endorsements. So what were the endorsements of the players in the NBA? Also the salary. So what were players being paid, and then their actual on the court performance. So the way I started was I had to write some of this code initially myself. And so let me just show you a couple of these examples here so you can see if you were going to build something yourself from scratch that talked to Twitter or Wikipedia. These are a couple examples here. In the case of Wikipedia, one of the things that I had to do was I first put a documentation aside so that I knew what was the URL that I needed to talk to. And in this case, this is the route, right? It was Wikimedia API REST, and then I had to construct this URL. So the way I did this was I created a base URL here, which would be the same for all Wikipedia users. I wrote a function that constructs a URL, and then I go through here and I return back the JSON payload. Now, one thing that I also had to do as well was add a little bit of a sleep inside. Because in general, you want to be careful about calling against an API in that if you do it too quickly, sometimes they'll ban you. So I wanted to be like not hammer Wikipedia with too many requests. And then I create a data frame of the page views here. And that's it. That's really the collection process. Now, one thing I discovered was that I wanted to make it user friendly to collect the URLs. And so I wanted to take a name like LeBron James and then put that into a handle. So in this case, I put a underscore here inside and I appended it to a link. And what this does is, in case I have some kind of a name collision, that it would automatically add the word basketball to it. And the reason that I needed to do this was that I had to write a function that attempted to guess the correct Wikipedia handle, because a lot of times you'll have a person with the same name. It'll be there was a football player called Anthony Davis, and there's also a basketball player who's currently one of the best basketball players in the world called Anthony Davis. And so if I just type in Anthony Davis, then it could give me two, and then I needed to figure out a way to automatically correct that. So with Wikipedia, they'll actually disambiguate by putting a name in there. So just the reason I'm bringing all this up is that these are the kind of things that you have to do. And if you want to play around with this code, you can run it yourself and collect social media handles. But a lot of time when you're going through and you're building the code, you're going to have to account for these edge cases because someone hasn't done it yet, and so you have to handle that code yourself. Likewise, here's a Twitter example here. So I wrote a function that goes through and uses the Twitter API to get the information about LeBron James. So, how many people are following him, how many people are retweeting his comments, and then you can see you can start to do descriptive statistics. So again, I don't know exactly yet what I'm trying to find, but I first need to collect the data in a way that's easy to pull it into a data frame. Once I've done that, then I start to merge the data frames together. So in a typical project like this, what I would do would be to have some kind of default entry points into the project. So in this case, I would have pandas, maybe some statistical modeling, import Seaborn, things like that. And then I start to make instances of each of these data frames. So in this case, I could go through and grab the attendance data. So you can see that these are the amount of people total for the year. I think this was 2016 that attended games. And then also it shows average attendance. I have some endorsement data, right? So this at the time was how much money he was paid in salary, LeBron James, and almost how much he was paid in endorsement. So you can see that they're getting paid more money in endorsement than they're getting paid in salary. And then evaluation. So here's the teams they're on. Here's how much they're worth. So in this, well, we don't know now. New York Knicks might not be worth that much more money anymore. But at the time, the Knicks and the Lakers were worth a little over $3 billion. And then salary, here's an example of a salary, the player impact rating. So again, these are all just metrics and stats and information that I pull into separate data frames. And then once you go, and then ELO is like a strength of schedule metric. So it shows how good you are in comparison to other teams. So once I've got all this stuff going, now I'm ready to do EDA, right? So you can see the first part here, and I'll maybe go back to this again, is that this actually took me, for this particular project, it took 3 months. I wasn't working on it full time, but I was working maybe, let's say 20 hours a week, collecting data for 3 months. So in the real world, if it's not a Kaggle project, it's not like you can just grab all the data that's interesting to you and just get it. It's going to take some work. And so this took a lot of work. Now the good part about it, though, is that I did find some things that I think were very interesting and even led me down other pathways that I wasn't even considering. So I think this is a good way to think about things, is that you're an investigator, you're thinking through how to collect as much information as possible. Especially, I think it's interesting to collect things that people have not found before. If it's already been collected and it's in a Kaggle project, it may not actually be that interesting. It may be interesting to combine Kaggle projects, but a lot of times if you hunt the data down yourself, you get some very powerful results. So went through here, collect all this stuff. So the next phase would be the EDA phase. So what are we doing in EDA? Well, it stands for exploratory data analysis. So we don't even know what we're looking for. We're just kind of like a detective looking for clues in the data. So what I do is I merge these data frames together. So that's typically a pretty good technique, is collect a bunch of data frames, start merging them together. You can see I take the valuation data frame and I merge it with the attendance. Now I have a bigger data frame, right? And so I add the columns. And you do want to have a unifying link. And so in this case, it's the team is the unique ID that merges those two data frames. Next up is a section on correlation heat maps. And this is a pretty common approach to start to also do some investigation, is to look at, let's say, in this case, which columns are correlated with other columns. And so we could see that, for example, the valuation of the team here, this would be how much the team is worth, is actually correlated with, let's say, the average attendance in millions, right? So which is intuitive, right? You would think that the more people attend to the games, the more the team would be worth. And you can even do this into a heat map. And the way you do this is with SNS, so seaborne heat map. And this is a pretty common practice when you're first starting out, is just do a heat map. And again, this is like, imagine you're a detective and you're putting you're fingerprinting or you're putting dust on something to see what's happening, right? This starts to show you the initial relationships. You can also obviously just look at the correlation data frame. Now, if you want to get fancier here, one of the things I like to do is create pivot tables. And here's an example of a pivot table that has the team, the valuation, the attendance, and you can start to kind of build this into maybe a richer visualization and see like, this is interesting. I wonder, and these are all of these. I think if we look at this bottom axis here, this was, the total attendance in millions per year, and then this is the valuation. So you see there's obviously some outliers here that are kind of popping up. Like, for example, I think this one is Chicago Bulls is an outlier. You've got what else do we have here? We have here's a couple right here too, like the Clippers and the Knicks. So you see they don't necessarily fit the pattern, the color scheme of everybody else. So that might be something to investigate. Another thing you can do when you first start doing the exploratory data analysis is to just use regular linear regression to just start to test some ideas out. So we know that there was a relationship, the correlation, right, which is a signal between the valuation of the team and the attendance. So what we could do is just do a linear regression. So this is in Python how you would do that is I would put in that data frame I created and then do a linear regression that says, does the valuation of the team predict attendance? And if I print this, we can see that I have an R squared of 28%. So you can see that there is something going on. I could start to create maybe a linear regression model that uses this valuation to predict the total attendance in millions. And if I look at the residual plot, if I say SNS residual plot, one problem though, if we were using traditional like statistical techniques, is that you see that there is some clustering here, right? So there's some clustering that shows up here that potentially it looks too uniform, and so the data is, maybe we don't have enough data to do a traditional statistical model, and then you could also go through here and maybe do a prediction and kind of look at what was the actual predicted value, and then what was the so it predicted. In this case, we were predicting the valuation, I think, and then this is actually the value. So we can see like not a great model. So then if I go through here and I do a Seaborn plot, I can actually plot it back, and you see that the valuation of the team and the predicted valuation isn't that great. There's something. Well, first of all, one of the things that's going on is it looks like there's a nonlinear relationship with the valuation of the teams. So this it's not that we're necessarily trying to create a model yet, but it just kind of gives us some intuition for later, maybe what we would want to look into. And so my intuition with this shows me that it does appear that there's some kind of a nonlinear relationship here with the valuations of the teams. And also, I can look at metrics like root mean squared error. So that doesn't give me enough to really know anything yet, but it gives me some ideas. So then I'm going to keep adding the data sets. And this one, again, is the ELO data set, which is the basically strength of schedule. So this is like a true metric of how good a team is the ELO. And so I, again, add this to the data frame. And then you can see, here we go. Here's the ELO. I also can do a correlation heat map here. Here's an example of it. And then I can actually plot things out here. And what we see is that there are some slightly different variations between the different conferences in the NBA. So the Eastern Conference, the Western Conference, and there's like the Western Conference is slightly better in terms of the score, and also the total attendance doesn't necessarily seem like it's that linked together with the ELO, and we can start to do a group by operation here, and you see that the median ELO for the West is a little bit higher than the East. And also, if we group by, you can see that the attendance is also a little, the average attendance per year in the NBA is also a little bit higher for the Western Conference. So if I go through and I try to do a regression against that, what we see is that it's actually, there's a signal, right? So we can use how good the team is to predict their attendance, but it's a very weak signal. So then I would think maybe I need to add more information to this to start to create a prediction. So then what I do here is I add in additional variables, and I add in something that I wasn't even considering before, which is the prices of housing and statistics about how many people live there, right? And so what I added here in particular was the median home price in millions. So if I go through and I do another, you can see what the columns are. We have attendance, the valuation of the team, how good they are, the population, the median home price. And if I add in if I want to predict the valuation of a team, and I want to say the county population plus the total attendance plus the median home price, and I put in that same data frame here and I fit it, one of the things that we see is that I have a dramatically different prediction accuracy now. Is that it looks like the home prices add a lot of signal. Now we have R squared of right around 80%. So we have a pretty good, and if you look at the p-value as well, is within acceptable range as well. And so we've now discovered that there was something else going on that's leading to the valuation of the teams. It looks like a lot of the reason why a team is valued highly is just where it is. So even though there's signals like the attendance or there's how good the team is, they're not as strong as actually other signals which include the attendance and the prices of homes. So what I can do, and I'll kind of skip this next section here, is start to use other techniques to kind of tease out this information. So what I'm going to show next here is a k-means clustering example. And the whole idea behind k-means clustering is that you're using unsupervised machine learning to really discover things, right? And so, a really good example here is let me just go back to the sketchpad, and I think that you really see this a lot in the real world, unsupervised machine learning, and for example, if you have a grandparent or a parent who says, be careful who you pick as your friends, this is important because the way that k-means clustering works is fairly simple, is that you find different points on a graph. Right here, here's a two-dimensional graph, and once, let's say that there's a cluster here, is that inside of this graph here, the center point, let's say these are all next to each other, that's one cluster here, and then we find another cluster here, is this could be, let's say, apples, and these are bananas, right? These are two kinds of fruits. I'm so bad at spelling banana. Let's just say that's bananas. Hopefully I didn't mangle that. But inside of here, the center of this is the centroid. The center of this is really the label, right? So if everything around you is an apple, or likewise everything around you is a banana, then you're basically able to say that, yeah, that's probably that label as well, banana, right? And so this is really the concept, is you're finding who's around you, and then you're inside picking the center of that, and then from there you can make a prediction based on what everybody else is. And so that's really the core concept behind k-means clustering. And so this would again apply to, you see this a lot actually, is that well, let's take basketball for a second. Is if I wanted to pick in basketball, who are all of the people that make blocks, right? Let's say that we had a cluster, and these are all people that are blocking the basketball, or you had another cluster, and these are all people that have, let's say that they block 10 blocks a game, 10 a game. And then over here you have people that are scoring, 30 points a game, and maybe you have some other things as well, like they do a lot of assists. you can discover that there's essentially a hidden label inside of here, and so in this case, one of the hidden labels could be that everybody is very tall. And in fact, that is one of the things that you'll discover about the NBA is that there's actually a perfect linear relationship between how many blocks you score and how tall you are. So it's not a surprise that tall people are good at the NBA. And then here, one of the things you might discover is that, I don't know, maybe like there's a perfect like height weight situation. So you could discover that everybody in here is 6 foot, 6, and they weigh 225, right? Like maybe that's one of the things that you discover. So it's a way of really it's actually almost magical, is that you can discover these relationships with people, and then the other one as well, and this is the part that I mentioned about who you associate with. And your parents would tell you this, hey, pick the right friends. Is same thing as if and we see this unfortunately a lot in politics, is you have somebody that's a criminal, right? Here's a criminal, or an organized crime. You have a criminal, and then inside, if there's, we don't know yet what this person is, but everybody around them is a criminal. Well, it's likely that they may also be a criminal, vice versa, if everybody around you is, winning, let's say, a Nobel Prize, right? They're let's just take Nobel Prize, right? These are scientists that are doing research that helps humanity. Well, if somebody is associated inside of this, right, there are a lot of the same characteristics. They work at a particular university. They are a certain age. Maybe they're they're studying a very interesting field, a challenging field. Then you could say that the emergent property is that maybe they're genius, right? They're genius level people because they have all these things in common. So that's really the thing that's interesting about k-means clustering, is that it discovers this label for you. So if we go back to this on our chart here, here's a good example of something I did that looks at that kind of a relationship. So let me make this a little bit smaller. So this particular graph here is actually a graph where I took, we'll show maybe right here. I took the rebounds, I took the points, so those are two values, and I also took the assists and the blocks, right? So those are 4 different categories of measurement. And so what I did is I used k-means clustering, and I collected all those things together. And what happened was it created these different categorizations for these players. And so what we saw is that this is a facet here that shows what I would say is the emergent label. Is these are, at the time, were the best players in the NBA, right? So we have, and maybe I'll make it a little bit bigger now that we've seen that. And so we can say, the best players in the NBA would be, at the time, 2016, I think, Kevin Durant, LeBron James, Blake Griffin. So how do we know? Well, it's self-evident now, because look at the circle size, that they're all doing a lot of assists right here. So the circles are really big. Plus, you can see that the points, or this is points, the farther to the right, the more points that they have. So they're in their own category. And also the blocks, you can see that the blocks are also so they're every single thing they're good at, right? But then if you look at this other cluster of people, what you can see is that this DeAndre Jordan here, Tim Duncan, there's something different in that they're still good, right? But they have more rebounds than these. They're slightly more weighted towards different categories. So in this case, they're very good at blocks, right? The color is richer in terms of how red it is. And so what we can see is that, in fact, These are very tall players. This is the last year that Tim Duncan played. He was one of the best players in the NBA. He was 7 foot tall. This DeAndre Jordan, I think, is like 6'11" or 6'10", tall player. They're exceptionally good. They're very big people that are also very good. And then we look at other categories, and they're also slightly different, right? So we have, in this case, we have Steph Curry, who's one of the best players ever to play, Chris Paul. And look, the circle is very big because they are doing a lot of assists, right? So really what happens is that I created these labels here, and so it's up to you as the data scientist to decide what label you want to associate with each one of them. But it's an emergent property. You can't ignore it, right? You can't ignore the fact that why did all these players collect together? Well, because they're the best. And then why would all these players collect together? Well, they're the big people that are the best. Why did all these people collect together? And then likewise, if you want to look down here, there's also players that are, maybe they're good at blocking the shot, but they don't have that big of an impact. They're like more of like that you put them in for defense. And then this one was, this was actually the year Kobe Bryant was injured, right before he quit, I think. And he had a very limited role, right? So had almost no impact on the game because he was injured at the same time. So this kind of data visualization can be very powerful in you discovering the next phase of what it is you want to do. So let's now go through and take that other data that I was working on and start to do this same technique. So how do we do this? To start with, you need to convert the text or get rid of the text attributes, or either convert them to numbers before you do the clustering, because everything has to be numerical. And so in this case, what I do is I only grab the attendance, the how good the team is, the valuation of the team, and also the median home prices. Next up here, we do this, and I say from scikit-learn.preprocessing, have min-max scalar. And what the min-max scalar does, if you see, I just print it out here just so you can visualize, is it takes everything and it converts it so that it's in the same range. So if you had two people that were talking about running, for example, and one person was like, hey, I ran 50K. And then another person says, oh yeah, I ran 50 as well. But they're talking about 50 feet. These are two totally different things. 50K is very difficult. 50 feet is not difficult. And so you need to scale things the same, right? And so all this does is take those values and put them all between 0 and 1. And so that's necessary in order to do the clustering. And then next, you would import the, say from scikit-learn.cluster, import k-means, and then assign some number of clusters, and then fit that to a variable. And then if you want to, you can also put that onto the data frame. That's what I typically do. So if we go through here, and I create this cluster, and you can see I assign the cluster value on the side here. So we've got 3 clusters, and everything inside has got some kind of a cluster assigned to it. And there are some techniques though. So you may have wondered, like, why did I pick 3? So there is a little bit of a science approach to it. Is like you can change this yourself and decide how many clusters, but you also can look at some visualization techniques. And so this one is a called Yellow Brick, and it's a tool set that lets you kind of diagnose the different clusters, and you could measure the distortion score inside and how long it takes to get there to kind of decide how many clusters to create. That's one way to do it. You also can do your own elbow method. Here's an example where you can go through and do your own elbow plot. And we see that this particular distortion here is it would be a good elbow, right? It's like three seems about right, where it's the number of clusters and the distortion. That's typically where you want to pick. It's just a guide. It's a guide. It's not like a hard and fast rule. You can also do a silhouette plot. Here's an example here where you do a silhouette plot. And this one, what I do is print out inside of here where people are in accordance with the silhouette. So you want typically the clusters to be mostly the same size if possible, although this is a very small data set, and you want them to be past the silhouette. So there's a bunch of techniques you can do to help you pick the right cluster size. You could even go into there's k-means clustering, and then there's also hierarchical clustering, and I could even go through here and print out the difference. And you can see that in the terms of k-means clustering, it does look like it's better at grabbing the cluster data versus the agglomerative clustering. It doesn't look like it's as good at separating things. So now that I've got that data, this is where we start to get into the visualization. And that's what really the clustering does, is it allows you to get into more advanced data visualization techniques. And look, if we see 3D scatter plot 2016, 2017, what I do is I create a three-dimensional plot that uses all of this data in one diagram here. And let's look at the different axis. So we have on one axis, we have the ELO. So the higher up you go, the better you are as a team. And at the time, the Golden State Warriors were exceptionally good. They beat everybody in the NBA. Likewise, the New York Knicks and the Lakers were very bad teams at the same time. But what's interesting is that look at the valuation. This bottom column here, it clearly shows that how good you are doesn't predict your the valuation of the team, right? We know that there's something else going on. And if we look at this, which is the median home price, so the more higher you go here, that the higher the median home price is, you can see that in fact the price of real estate has a significant role in the valuation of a team. And also we see that there's different clusters here, and we can see that we could write our own label, right? So we could say there's teams that are in geographically dense regions that are worth a lot of money, but also are very poor teams. And we can see that there's maybe teams that are, like good teams that are typically more related in anywhere from median real estate to expensive real estate. And then you've got these kind of teams which are poor performing teams typically, or lower performing teams who have also low valuations. So you could decide what you want to call the label. It could be, it's up to you as the data scientist to decide what the label is. But you could then start to make decisions using this data. So you could say, for example, the Brooklyn Nets or the Indiana Pacers or the Sacramento Kings, maybe that's a team that you would want to invest in because they're worth their valuation so low, but they have some potential, and this might be a good team to invest in, right? Versus if we look at something like the New York Knicks, that would be a very expensive team to acquire. And so you could potentially, even if you look at the valuation, you could acquire the Philadelphia 76ers and the Orlando Magic and the Phoenix Suns for I think less than you could the New York Knicks. So you could buy three, and then you could try to make all three of those really good teams. So just a couple other things I'll mention as well that are techniques that can help with scikit-learn is you can do things like principal component analysis. And what that does is it reduces the dimensions first. And these are just some examples of how you do that. You also could do feature ranking. So here's an example of how that would work is you could use different rank which features are applying the most to the model, and there's an example of how to do that. And if I go through and I run that, I think Well, this one, they might have changed the API. We don't necessarily have to do that. I have some stuff at the bottom that I'll show you that does similar things. The You can also do classification. So you could even convert the model into a different kind of a prediction. So you could say, for example, I want to classify the teams that are good teams versus the teams that are bad teams, right? And so once you start to get this data, there's a lot of things that you can do to it. Another thing you can consider is maybe using AutoML. There's a lot of AutoML technologies, including Ludwig is a good one, scikit-learn, AutoML. But again, you can also decide, instead of creating some kind of a model, you can keep going deeper. So one of the things that I discovered, if we go back here again, is that this is one of the most interesting parts of the problem. So maybe because I'm doing this for myself, I'm just trying to explore an interesting story to tell or do something interesting. Maybe I just stop the MBA for a while and say, okay, that was interesting, but I'm gonna now go into home prices because home prices seem interesting to me. There's something weird going on. So then what we could do is go to this next section, where what I do is I use a library called Plotly. And I think Plotly is one of the more interesting libraries for data visualization. And at the time, I think this one is one way that you can load Plotly. I think it's much easier now. Like, you don't have to do it all this stuff. I think it's an easier way to integrate it. But what I do is I add in a bunch of boilerplate code here, and I put that same information into a new data frame. And what this data is actually data from Zillow, which is the real estate company. And I look at all of the data they have, which is from 1996 until I think 2016. And what I do is I clean it up. So we're kind of back to where we started again, which is that when you first start a data science project, even if you're going off of on tangent a little bit, you're going to have to change things around and move things. And so in this case, I renamed the data a little bit. So region name, I change it to zip code because that makes more sense to me. I also format the strings so that they're numerical, and then I do a print of it, and you can see, like, now we have zip code, right? So this looks good. And then I also start to look at the data just numerically. So one of the things that I do is I look at the median home prices in 2017 in the United States, and you can see that there were 183,000 would be the median home prices. Now I could even add something in here, and we can see what is the max home prices. And so if I say df.max, and I go to max prices, we can also do that, max prices, and then say .tail, and this should show us the highest prices. So we also see that there was homes that were, I think in this case, this is 60, so there's homes that are 6.5 million, right? In different zip codes. So there's some zip codes where the prices are around 6.5 million, but the median is 183,000. So what I did also is I looked at some different regions in the United States. So here's Marin County, San Francisco, Palo Alto. These regions are interesting regions because these are some of the most expensive regions in the United States. And in fact, the income inequality in particular in this area is even higher than third world nations like Nicaragua, Nigeria. There's a lot of interesting data to look at from a data science perspective. So what I do next here is I create a plot that shows the Bay Area prices from 1996 to 2017. There we go. And what this shows us is that there is some very troubling trends that in the Bay Area, and one of them is that if you look at San Francisco in particular, you see that the San Francisco has got exponential growth right from about 2010 or so, 2009 there was a crash, and things were even before they were only going up a little bit, but right after the crash, exponentially going up. And then if you look at places like Marin County, even though it's a very expensive place to live, it's not even close to Palo Alto, right? This is where you have companies like Google, Facebook, Apple, all around there, and they're it's complete uncontrolled exponential growth as of 2017. And so this is actually pretty interesting, and maybe what I want to do is explore that a little bit more, so I can do the same technique that I did before, right? Which is look at pre-processing the data. So I'm going to go through here, do scikit-learn, describe it, and then get into the min-max scaler here, do some clustering, and you can see that I'm able to, I think, assign a cluster with each of these regions. So the other thing that we can do is create a 3D plot here. And this is one of the things that I think is very powerful about Plotly, is that when you do clustering, a lot of times, if you put it into a three-dimensional plot, you can, and especially if it's interactive, you can add a ton of value to interactive 3D plots. So this here is a appreciation ratio. This is a 1996 price. This is a 2017 price, and then I also create a text field called city, zip code, and then appreciation ratio. So why do I do this? Is that if you see up here, I create this particular value, and look what I do is I just take a bunch of the columns as a string. And so why would I do this is so that when I hover my mouse, it will add the annotation to the hovering. So then I can easily see the things I care about. Which city is it? What's the zip code? And how much did it appreciate in value, right? And so if I go down here and I run this, hopefully it doesn't take too long to run. Here we go. Yeah, this works pretty well. Is that I get a very interesting plot. And what this plot shows me is the, let's go here. It shows me that there's some weird things happening in real estate in the United States, and in particular, let's make this a little bigger. Look at this. We have, there's a TV show called Beverly Hills 90210 when I was a kid, and it was about the richest people in the United States, and you can see that 90210 is in fact still the most wealthy zip code as of 2017, end of 2017. You can see that in I think it starts at 1996, the home price was 1.4 million, and then it's gone all the way up to this value here, which I think is the Z is a 2017 price, so it's 5.67, and so the appreciation is the last thing hashtag. So it's gone up 4 times. It's 4 times what it was worth 30 years ago. And if you look here though, right below this, Palo Alto is right below. So basically, Palo Alto has gone up 6 times in appreciation though since that time. So you can see that the median home price for Palo Alto here is extremely high, and it's appreciated. I think it would be $4.18 million and we also can see very strange things, right? So we can see that this cluster would be maybe very wealthy homes, and then we also see this, which is that Jersey City, which is a suburb outside of New York. So Jersey City is literally right outside of Manhattan, has gone up 9 times in the last 30 years. So this would have been one of the best investments that someone could have made, is buying homes right outside of New York. So this is the kind of thing that you get when you do clustering and data visualization. And I didn't know it even initially. I was interested in this. I was interested in MBA, but then I discovered that all these teams were valued based on the real estate. Then when I start looking at the real estate, okay, there's something interesting happening. So I guess the big takeaway here is that this is a great way to explore data, is clustering, data visualization in 3-dimensional and especially interactive plots here. So let's keep moving through this notebook and see that another thing that you could do as well, in especially like data journalism, data visualization, is you also can just hand code. Once you know what it is you're building, you don't necessarily have to always pull the data from a data frame. In some cases, you can hand code each piece of what you're building. So this one here is a notebook where I literally put in all of the values myself just from a spreadsheet. I just put in the values myself, hand code them. And I'll show you what this does. Is this creates a plot that shows you the endorsement and social media power of the top athletes in the NBA. And so this is the kind of thing that you could put on 538 or Wall Street Journal or something like that. And if we look here, I can hover over these and I get all of these different attributes. And I can even toggle, and I can say, I want to look at only the Twitter information, right? So I want to see maybe salary and Twitter information, and we can see that in this one, that at the time at least, LeBron James made the most in salary, but his social media was at least for Twitter was not as powerful as Steph Curry. Probably a better one to look at would be to look at Wikipedia, because Wikipedia is probably a little better of a signal, because not every Twitter is a smaller market. So let's just look at Wikipedia and salary. We can see here that if I was the agent for Steph Curry, what I would say is like, hey, that he should be paid more money, because look, LeBron James gets paid $30 million, but his popularity is good, but Steph Curry's is the top. He's the top popularity. So the owner of the NBA team should give Steph Curry more money because he's making the Warriors more money. Additionally, if we look at the endorsement value as well, you can see that this blue factor is that he's getting paid less than LeBron James in terms of endorsements, but his popularity, if you look at, let's just take away salary here, and let's look at the Wikipedia and social only, you can see that in all of the social categories that Steph Curry has got higher ratings than LeBron James. So these are the kind of interactive plots that I think also can be very powerful when you're telling a story. And as I mentioned, you can build this. The reason why you may want to build it from scratch, like I literally put every single thing inside this plot, was that then you have total control over the thing that you're building, and that's just another thing to consider. So let's also kind of get into this concept of feature engineering. And so this is a picture from an O'Reilly book about feature engineering, and so this is, I would say, a very true example of what I just showed you. Was that a lot of times you start with the data and then you just go everywhere, and you don't even know where it is that you started almost, and then you get to the answer. So it's not a straight line, and one of the things that happens is that it's full of false starts, frustrating delays, infrastructure problems, a laptop problem. Your laptop isn't production. In the real world, isn't these like toy data sets. So some of the things that happen in a machine learning project is that you need to have a model, and you need to have features. And the model is a mathematical relationship between the data, and then a feature is a numeric representation of the data. So here's again a picture from that same book. You've got the source 1, source 2, however many sources, which we just went through, and you select and merge, which we also just went through. You take that raw data, you clean it, you transform it, and then you build out the features, and then you can do things like k-means clustering. But you have to collect it, merge it, clean it up, maybe turn it to a numerical format, and then you can do modeling. And then once you did the modeling, now you can get the insights. And so let's also take a look at this example as well, which is that only a small fraction of the real-world machine learning systems are composed of ML code. And so here's an example here of a small black box in the middle here. Here's a ML code. And you can see that everything around here is a large amount of data. So we've got configuration data, data collection, feature extraction, data verification, machine resource management, analysis tools, process management, serving infrastructure, monitoring, a whole bunch of things that are unrelated to machine learning code. And so that's why if you're too focused on only the machine learning, you won't have as much interesting insights that you gain. You also have to be aware of all the other things that we just talked about. So some of the takeaways here are that in the real world, the glue code, like all the stuff we just did, that's the sundae, and the machine learning is like the cherry on the sundae. It's only a little bit. So it's 5% of the code in an ML system. At least 95% is glue code. And so here's a picture that I saw someone build, which is that there's research, ML, AI, there's operationalizing machine learning, right, which is machine learning engineer, and then you have data engineer, which is distributed computing. And this is an example of somebody, this big data institute. And so a common starting point is 2 to 3 data engineers for every data scientist, and some organizations with more complex data engineering requirements, this can be 4 to 5 engineers per data scientist. So you can see why that even though people are called data scientists, that the word is a little bit of a bad word, because most of the work is not data science. And so I think it's better to be somebody that can do all those things. In my opinion, I think it's important to be able to do research, operationalize, and do distributed computing. So do data science, machine learning, and data engineering, I think is a much more complete skill set. So let's look some more at how you can do feature engineering. And so what the core concept here, and there's a link that you can take a look at. The core concept is this concept of machine learning explainability, and you could take some more information about all this. There's a whole article on it. But what I'm going to do is I'm going to bring in this FIFA data set that they bring here, and then I'm going to train a model on this. So I'll go through here and I train this model. Now I can install this library called ELI 5, so explain like I'm 5. And once we go through here, I can run this permutation and importance example. And so what it does is it shows me of the features that were used to predict who's the best player in soccer and FIFA. We can see that the most important feature it discovered was the goals scored, right? And so what this means is that that we're able to do things like look at also distance covered. That's the second most important feature. Yellow cards. So maybe the yellow card would show that there's aggression, right? Like if you're getting a yellow card, it's you have a lot of like your energy and you're trying to do things, free kicks. Now, if we look down here for negative features, though, we can see that maybe attempts would be one of the examples of something that is negatively correlated. So how would they figure this out? The way this ELI 5 works is that it takes out each feature and it reruns the prediction model, and then it figures out which features contributed the most to the final prediction. So this can be really helpful as well when you're kind of figuring out what kind of data to collect or what it is you're looking at, is to look at these feature importance to see either should I collect more data on this or am I adding things in that don't add to the prediction power of my model? And here is a example of kind of getting into some of the concepts in scaling. So in scaling, like linear regression, you don't need to worry about the features, but most of the time you have to apply scaling to fit the model. And so here's an example. Again, where I already went through this, I won't plot it again. But inside of this example here, let's kind of go through another plot. What we can see is that I can also take that same plot that we had earlier and I can bring it into this diagram. You can see that there's a lot of interesting things that pop out when you bring things into a interactive three-dimensional model. So this is something to think about in terms of any kind of a data set that you work with, is that maybe one of the techniques you always start with is as you're building your features, you're building things, you're looking through around, as you can use clustering plus 3D interactive visualization as almost like a default technique to explore data. So let's keep moving here and let's go to this next few other things here. So another thing to consider when you're building out and building your explorations is this concept of bias. So, do you have too many positive or too many negative examples? The classifier could always pick the majority class. Do you have mismatched sources? Is the training procedure focused on enough data? What about algorithms that won't work well with the data? So there's a lot of things to also consider outside of just doing the modeling. And so a few key takeaways are that there are some techniques that you can use. So like if you have 1,000 to 10,000, maybe you could try more complex algorithms. The more data you have, the harder it is to beat logistic regression. And then also neural networks can discover useful features and complex inputs, right? And so here's a cheat sheet of scikit-learn that you could take a look at. And this one goes through and shows you classification roadmap. This shows you a regression roadmap, dimensionality roadmap, and clustering roadmap just for the scikit-learn library itself. So if you wanted to use that initially to start to explore your data set here, if you start first, do I have more than 50 data? Okay, great. Am I going to predict a category? So like good or bad, or dog or cat? So yes. Okay, do I have the labels for the data? If you don't have the labels for the data, first you need to go in and you do clustering. So that's what we did. We went through and we did the k-means. If you do have the labels, then you can go through here and you can try this SGD classifier. If you don't have 100,000 samples, if you do, you can try this linear SVC, right? So a lot of times as well with scikit-learn, you can kind of go through a checklist and figure it out, what it is you're trying to build. So let's look at a couple of case studies on this and go a little bit further. So let's say that now that I know all this information about the NBA, I want to go through and predict a winning team. So how would I do that? Well, we could go through here and grab that data that I had before and just kind of print it out. So I have a bunch of data inside of here, and it's got things like the position, it's got the salary data that I collected, the page views, the Twitter favorite counts, retweet count. So next, what I'll do is I will create a new feature, which is a winning season. And notice what I do here is as I go through and I create a function called winning season. And all it does is it takes a win and it says if the number here is over 42, return back 1, otherwise return back 0. So basically I'm binning the data. If it's over 42, it means it's winning season. If it's under, it's a losing season. And then what I do is I create a new column called winning season, and I look at the wins. I say data frame W apply winning season. So this is a very powerful technique in pandas, is that you can write a function, you can apply that to every single row in the function, and then make a new column of data. And then I scatter plot this out. And what we can see here is that that I also could even start to do some exploration around this new feature that I created. So we see that the age of the player doesn't really look like it's related to the wins, right? So if I wanted if my hypothesis was that players as they get older are less likely to have a winning season, that doesn't appear to be true. We can see that it looks like there's no real relationship. So maybe what I can do next year is start to build this out into a model. And so I take these values, so these are the numerical values, and I put the features together, which are age, points, salary in millions, page views, Twitter favorite counts, and then I think this is turnovers. And then I create classes, which is a winning and a losing class. Here we go. And then I shape the data here. And then I say from scikit-learn.model.selection, import train test split. I create this training data. And you can see that what this does is it pulls out 25% of it so that I am able to validate my model against that later. And you can see that I originally started with 239 and now I have 177. So next up, what I'll do is I'll use logistic regression. And a logistic regression is a classification, right? We're just going to say, are you a winning season or a losing season? So we go through here and we run this, and I train the model. I say model logistic regression model.fit. And now that I've got this, I can actually go through and look at the report. And this report could go through and show me how well it is at predicting a winning season and a losing season, and how good it is at false positive versus false negative, and vice versa. And if I go through here and I do feature ranking with Yellow Brick, here's an example, that for some reason they must have changed that API, so I'll just go to the next one. Is I'm going to explain it with this other library called SHAP. So we talked about this earlier, that there was ELI5. Well, this is another one that you can use, which is, in fact, I think I'm just going to delete this, because since they changed it, I will not use this library anymore. There we go. Gone. There's a better library. So this model, SHAP here, what it does is it actually will visualize all of the features that were used in the model and show the importance. So XGBoost is a classification algorithm. So I can just say, okay, hey, I want to run XGBoost here, and what it does is it shows me that the higher values here are red, so we can see that salary, social media, turnovers, points, these are all contributing factors to whether you would have a winning season or not. And then the lower values show up here. So if I print this out, we can see a couple plots here that are pretty cool. So in general, this is probably the best one, is that you can see that page views, Twitter favorite count, salary, these are all factors that we could use to predict whether a team was having whether a team would have a player would be on a winning team or not. And so this is an interesting model in a way, because you could see, for example, let's say you were a sports bettor and you wanted to kind of find a new thing that could discover, how to make an accurate prediction model. You would look through and say, look, in fact, the things that are on the court related, points, age, and turnover, these have nothing. These are not as predictive as things that are other metrics, like how much they get paid, how popular they are on social media. Those are actually signals I can use to predict whether they're going to be on a winning team or not. And so the same thing, we could go through and we could use our ELI 5 example here and do the same thing, right? And we could go through and predict this. So you can see there's a lot of, and we can see here as well with this one that the points, salary, page views, those are the top in this particular model that we used. Those are the top values. So we've gone through a lot of stuff. We collected the data, explored it, build like data visualizations, then finally got into doing predictions. Another thing that you might also look into is H2O. And so H2O is kind of an interesting library because it does complete AutoML. And here's an example here of this library called H2O. And if I say from H2O import H2O AutoML, one of the things I kind of like about H2O is that you can basically just put in the data and it will automatically figure out the right algorithms for you. And so this example, it might take too long, but I'll just run it and see what it does. What it does is it actually shows an example of that it spins up a cluster, and then it will go through and just pick all the different kinds of algorithms that it can find, and then shows you which algorithm is the best algorithm. And I think this is also one of the things that we're seeing a lot, is that a lot of this AutoML technology can play a role in your project. So once you kind of know what's happening and you know what the core features are, and maybe you even have a story that you tell, maybe another thing to consider is why not also use AutoML and then further hone down your model and pick it. So I'll let this run for a second, but I'll show you another AutoML library that you might be interested in called Ludwig. And so this is yet another library. So while that's running, Ludwig is this Ludwig library here, which I can put into chat, is pretty interesting because it does all kinds of different automatic AutoML. So it can do text classification. So if you're doing some data journalism, for example, this could be a very interesting library to play around with. It can do extraction and classification. It can do entity recognition tagging, and the way it works is you define it. You say Ludwig experiment. You pass in the sequence tags, which would be this stuff right here, and then you give it a model definition. So you say, I want to, here's my input and here's my output. I want to tag this data, or I want to do natural language processing, right? So I want to figure out the intent of this particular phrase, right? And I can go through here and do the same thing. So I think these are also emerging tools that are happening in terms of data science. Is that why write a bunch of code that you don't need to write if you can at least initially use a tool like this that can automatically find all that for you. And again, I think AutoML could be a very powerful technology to use for this. And not only for the text, but here's another example that's maybe a little bit easier to look at, is that in terms of image classification, which is a pretty classic problem to understand, is that you have pictures of something, like in this case there's a car, a dog, and a boat. They're already labeled. They have maybe a CSV file that each of them are labeled. You just put the directory on your computer and you put the path in, and you could say, Ludwig experiment, create a classification. Here's my labels, and then here's my model definition file, and then I can go through and train it. So these also can be, I think, very interesting, these AutoML technologies inside of the thing that you're building. So I think if you kind of wrap up all this stuff together, let's maybe summarize this. So in terms of data visualization here, we've got, let's go here. We have the ingestion phase. We have the EDA phase. We have the modeling phase. And then we have the conclusion. And we mostly focus on these two, but as I mentioned before, there always is like there's like a feedback loop between this, and a lot of times as well, there's a feedback loop between the conclusion and exploratory data analysis and modeling. So this phase is oftentimes 80% of the problem is do I have the data? How do I collect it? How do I move it together? And then I would recommend that a lot of projects that looking at using clustering as a data visualization technique, especially if you use clustering with a 3D plot. It's a very interesting way, either a 3D plot or a faceted plot, like the other plot that I showed. These are great ways to kind of visualize the data and start to find patterns. And once you do, and you kind of know what it is you're trying to do a prediction. So like at the very end, I guess the things that I was starting to model were that I looked at home prices, right? So maybe I could have created a model that showed home prices, or I guess I could create one income inequality, right? That's a big problem in the United States. Income inequality. The other one could be that we could look at the NBA predictions. So you can NBA wins. So once you start to get into the ingestion EDA, it could be that you have multiple models that come out, like home prices, income inequality, NBA wins. You could also look at endorsement for players, like who are players that should be paid more money, and they're underpaid. Players pay, right? And then you potentially could have multiple stories that you tell. In fact, or even an article. You could write a whole article about this. Is that I don't know. You could say trends in income inequality, right? That's and so you could say even that there's income inequality even in the NBA, even in the wealthiest regions, that it's very easy to not pay people what they're worth and have some people get all the money and other people get less money when their merits are are the same or better. So in the case of Steph Curry, likewise in the home pricing, you could look at it and say that if you're renting a home and you live in the Bay Area, the wealthy people, as we saw from the picture, they get very rich, and then the people that are renting get very poor. And so, how could you write a story about that? Like, should people move somewhere where they're not giving all their money to the people that are already rich? Or in the case of NBA wins, you could look at the fact that maybe one of the ways that a team could predict who they should add to their roster is look at what they were paid before, how popular they are on social media, and make that potentially more important than maybe the stats on their team. So there's a lot of interesting articles that you could write as a result of this, and a lot of it is if you have an open mind about not necessarily having a conclusion you want to get to at the beginning, but starting with ingestion, starting with exploratory, and then the data will start to show you all the different things that you can find. So, for example, I think probably a topic that's probably fascinating as well is if you look at which regions of the world have done well with COVID-19 and which regions have done poorly and why, right? And you could say the United States, in my opinion, has done very poorly, and so that could be a data journalism story. Is like what are the different things that are factors, right, and that cause one place to have better impact than another. So I think this formula is a very good formula for lots of different projects, and I think also that it's important to do something that you're personally interested in, and then that's how you can, I think, come up with the best kinds of stories that you write, and the best kind of data journalism and business analytics and data sciences. So maybe I'll do one last diagram here. Is like how do you pick a problem to work on? So how do you pick the right problem? The right problem. So one way to do that would be to have, is it something that you're passionate about, right? And so I've heard people say different things about a career, like you should pick something that you're good at versus something you're passionate about, or vice versa. But in terms of data, we'll call this data science, for sure it's better to pick something that you're interested in. So music, or arts, or sports, or science, or literature, books. I've seen people, for example, like try to figure out who is the author of a particular book, right? Or in sports, right? Like the wins, or in music, can I discover like types of music? So I think when you're building these personal projects, one of the most important things to do is, do you care about the thing you're doing? If you don't care about it and you just grab something again from Kaggle, I don't think you'll have as good of an impact as if you truly want to look into it and see, like, I want to discover something about music, or discover something about science, or discover something about books, and then use the techniques that we talked about before. Grab as many data sources as you can, start to do these plots of visualizations, and then when you start to discover things, follow up on the things that look like they're correlated, do data visualizations, and then eventually you can also build it all into some kind of an article or a report. And I think a good example that I could show you that's somewhat related to this is that I wrote an article recently on my own website here that's called Data Science Meets Intermittent Fasting. And so what I was showing here is that this is a very simple plot. Like it's not it's there's not much data, but what it showed was I had collected body weight for the last, like, I don't know, maybe 10 years or something. So let's just say roughly like around, yeah, roughly around 10 years, eight to 10 years. And I experimented with my own body, right? And I looked at different periods of my life when I was getting MBA, when I was doing lots of exercise. But one of the things I discovered was, at least for me, and there's some science behind this, is that if I don't eat food until later in the day, if I have a large period of time where I don't eat, that my body weight goes lower, just immediately goes. I'm much thinner, and so that's another good example. Is I was personally interested in figuring out about what are the best techniques to make you healthier and have a good body weight, and I used myself. And so I was able to, and I probably will keep working on this problem, and maybe find different foods that also are, make you healthier or unhealthier. So I think when you're passionate about a particular project, and I'll throw this into a chat here. When you're passionate about a particular project, I think that's really where you can start to really find some interesting things. And I put some links down here too. Like, for example, there's some citations here about, and this could take me years to look into this, is like that there's certain foods as well that the more you eat these foods, the fatter you get. So potato chips, French fries, the more servings of those you have, and same with sugar sweetened beverages. We know this now, that so if those are two data points, like maybe I could even predict my own body weight by looking at the types of foods I eat, and then also the duration that I would have per day. And so that's another data set here that shows that, in fact, there's some foods that add calories and there's some foods that subtract. So the more fruit, the more yogurt, and the more nuts you eat, the lower your body weight. Likewise, we know that there's a spike with what's the duration per day. If you eat all day long, it's not as good for you. So there's lots of ways to apply data science, including to yourself. And that's my recommendation: is pick something that you're interested in, and you'll find something.